the Sustainability Management Master's Program, you're answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
Welcome, Mohammed.
Thank you, Professor Sarkar. If I may share my screen now, I will do so.
Yes, we can.
Okay. Thank you, everyone, for joining. It's a pleasure having you here and talking to you. Can everybody see my screen well?
Yes, we can.
Yes. So, yes, today I will talk about wave energy, perspective on applications, technologies, and challenges. Allow me, please, first to start by talking about the Davidson Lab. I have this habit that, I like to introduce the department and the lab as well before I start any seminar. And then after I do that, I will talk about, give some, ideas about technology briefs about, wave energy, why wave energy, what it means, and, what type of wave energy devices there are, and what kind of barriers are there. Once I finish the second part, I will talk about our design of a 100 kilowatt wave energy converter. I will explain how the design process happens. I will also talk about challenges in the design and so on. So again, thank you for joining today, and I will start. So Davidson Lab is about blue innovation, I call it. The blue innovation because it addresses the highly specialized issues confronting naval architecture, coastal and ocean engineering, physical oceanography, marine hydrodynamics, and the integrated issues facing natural and human-made maritime systems. We do that through innovative technologies that tackle societal needs and vulnerabilities to challenges of different scales. The Davidson Lab started by looking at maneuvering ships, forces on maneuvering ships. Then beyond that, they built another wave tank towing tank rather, to look at seaplane design. Then beyond that, and every time there was a new challenge, we came up and we said, yeah, we can do it. We started a coastal program. Sometimes in 1970s, 1980s, we have one of the best coastal programs in the nation. And then, more recently, we started working on marine energy system. I mean, it's not like we haven't done any of this like in between, but really every time we started working on something, it was in response to some societal need and to address some challenges. Is the Davidson Lab relevant? Yes, because of something called blue economy. Blue economy, as defined by the United Nations, is the sustainable use of ocean resources. And this is where sustainability of ocean resources is important. We use it for economic growth, improved livelihood and jobs, and ocean ecosystem health. We use oceans for renewable energy. We talk about offshore wind. Everybody's familiar with this. We're going to talk about marine energy systems, wave energy, tidal, surface current energy, and so on. And there are more opportunities actually to use oceans for different types of renewable energy. We use oceans for food, fisheries. You know, a lot of people like fish, eat fish, so it's a big part. We use oceans for maritime transport. About 80% of international goods are transported by oceans or on ships in oceans. We use oceans for tourism. You know, a lot of coastal areas are, you know, very important for tourism in many different countries. Oceans are an important carbon sink, so we have to maintain oceans to be healthy because they can impact the climate change. We use oceans for waste management. You know, 80% of litter in the ocean actually comes from land-based sources. So in the Davidson lab, we address renewable energy, we address maritime transport, and we address coastal living and resilience. So, you know, that's why we consider ourselves relevant. When we say about blue economy, you know, worldwide, I think in 2018, it was 1.5 trillion per year. That's very significant. In, you know, if you look at the states like New Jersey, about 85% of the population lives in coastal areas or in coastal portions of New Jersey. You know, we like to live in coastal areas, but we have some natural hazards to have to deal with, including hurricanes and nor'easters and other storms. Mitigating these storms costs a lot of money. In New Jersey alone, it costed $4 billion in 2018. You know, U.S. Marine ships and so on industry, U.S. energy industry, U.S. defense industry are usually, or a lot of them happen to be in coastal areas. So coastal areas are important to the economy in the U.S. and in many parts of the world, and they specifically support a lot of people and jobs. What's unique about what we do in the Davidson lab of our facility, towing wave basin. We have a facility 100 meters long. That's very significant. Not what I mean by not many universities have such a facility. We could tow things at a very high speed. We have wave energy maker, unique wave energy makers. We could make waves up to 2 feet high with very broad range of wave periods between 1 and 5 seconds. Yesterday, I was talking to my colleagues at Michigan, and one of them was explaining how much our facility is better than their facility because they can only generate, I think, up to 2 seconds waves in there. They cannot generate 5 seconds waves or 4. So this is a unique facility that separates us from a lot of other places. What we can do here is different than what many people can do. You know the facility, but you also need to know about research vessels. We have 2 research vessels that, you know, place samples and observation stations and collect them on a regular basis from our coastal areas. We have drones to look at coastal erosion, and we have personal watercraft or jet skis in the common language also to perform research. The lab has its own high-performance computer. It's very expensive to maintain and to support, so we're moving to the cloud. Hopefully this will happen soon. But what we do, we can predict storm surge street by street, and you know, 3 meters by 3 meters. This is better than predictions by, you know, NOAA or something. When we say street by street, because their predictions are over larger resolutions. The way we do the predictions, we collect weather information and from Europe, from the United States, US, from Canada, and we generate our own perturbations. And every 4 hours, we run these weather models into our own simulations of ocean dynamics and so on to determine the wave profiles, the wind profiles, currents profiles over a large area of New Jersey and New York, and, you know, a broader area. But for now, we'll stress this area because this is where we do the high resolution. And then we use this, and we use some hydrologic forcing and so on to predict flooding street by street in different parts of New Jersey. You could reach that on SFAS, Stevens Flood Advisory System. We predicted 5 days ahead of time. You know, that's also significant because preparing for storms takes time, and preparing, to reduce the losses takes time. So it's good that we have these 4 or 5 days predictions. It doesn't help to predict things the day before it may happen, because you don't have enough time to prepare. Okay. Our focus research areas. So I'm gonna talk about here, excuse me, maybe the music might be too loud here, but just to show you some. This is our high-speed towing that we do. This is here another one of high speed in waves. And these measurements are very important. We're unique to be able to do these experiments. This is on marine energy. This is, harvesting energy from tides. By this flexible motion, the water is moved into an area and then is pumped up that pipe that you see up there. And this is our flap that I will talk about it later on. I'll talk about marine energy in more details. We do coastal research. We look at storm impact. We do a lot of field work and also living shores. We do all of this when we talk about coastal research. We provide rather the New Jersey Coastal Protection Technical Assistance Service. We serve as a resource for coastal municipalities and state agencies that are concerned with preserving New Jersey's oceans and bay shorelines. We work also under the New Jersey Sea Grant Extension. We perform, research. We do shoreline evolution, hazard mitigation, coastal management, coastal policy, and related topics to coastal communities. And Dr. Miller, who leads all of this research, is one of the authors of Living Shores, where he incorporated ecological principles into engineering design of shore to perform shoreline stabilization. These are some of the work that him and his colleagues do. They go in the water to collect samples. This is in winter time, probably. These are our research vessels moving around to collect data. This one here. And samples from different areas. So I talked about the Stevens Flood Advisory System. This is the outcome. We do these calculations every 6 hours, 4 times a day at 8 a.m., 2 p.m., 8 p.m., and 2 a.m., where we calculate surface currents, wind profiles, and wave profiles. These are unique sets of data. We usually provide the output free. We have 1,400 subscribers who use the output. But if somebody wants the data, we charge for it. We charge anywhere from $20,000 and above, depending on how much data they need. This is, This is how we, when I say street by street flooding, this is what I mean, street by street flooding. Our most recent thing is the effort led by Dr. Tamimi on urban flooding. Storms happen very fast, especially in summertime around here. What you would like to do is to be able to predict the storm as it happens in an hour or so. And that's one of the things that we're planning. I hope we can buy this instrumentation very soon. Okay, let me tell you about wave energy. Told you about the Davidson Lab, I want to tell you about wave energy. Can we power the grid from wave energy? Let's talk about power density. Density is energy per meter squared, or energy per meter cubed, or something, or power per meter cubed, or power per meter squared. So if I take wind, a wind that's blowing at 9 meters per second, that is pretty high, actually, 9 meters per second. When I speak, probably, the air is coming out of my mouth at the speed of 2 meters per second or less. So you could imagine that 9 meters per second is significant. And you take 1 meter square, just frontal area, like you're looking at a wind turbine, frontal area, 1 meter square, that'll give you 470 watts. Okay. If you look at that has 470 watts, that's how much power it has, that 1 meter square. You cannot get more than that. If you look at waves, you look at a wave which is 1 meter high, that's about 3 feet. You look at a wave that's, take 1 meter of its width. And if the period is 10 seconds, that 1 meter square of the wave front has a power of 4,900 watts per meter. If I do the calculations, available energy per meter of wave front over a period of 1 year, that is, I take this, multiply it by the number of hours per year, I end up with 43,000 kilowatt hour per year. That's the amount of energy. If I have this wave coming regularly all the time, every 10 seconds, which doesn't happen, but I have a lot of waves. So if I compare this to the average energy use per household, it's about 10,000 kilowatt hour. That's probably on the low end. You could look at your power energy bill, and you could see that. So if I look at this, even with 25% efficiency, 1 meter squared of a wave that has a period of 10 seconds could power my house. That is very significant, because that's a lot of power in that 1 meter squared. That's much more available than wind at 9 meters per second. And at 9 meters per second wind, I would need 10 meter squares to get that much out of it. So if you look at New Jersey, it has about 10 kilowatts per meter onshore. The example I gave is 4.9 kilowatt per meter. So New Jersey has a higher, twice as much power per its waves as the example I gave. And that amount of power is much higher if you go deeper in water. That's about, in New Jersey, it's about 40 kilowatt per meter if you go a few kilometers in. So the power density of water is much higher. Why? Even though the water is moving at a lower speed, the density of water is equal to 1,000 times the density of air, and that's significant. Now, in that sense, wave power is much better. Where are we at this point? By 2030, it cost about 3 cents per kilowatt hour in most parts of the world for wind. Wave power is still much more expensive to generate. So what we need to do, we need to do innovation, we need to invest, and we need to give it time. Wind power research and wind power development started in the 1970s. But back then, they didn't have the composite material that allowed them to build light blades that can be very long, light but strong blades that can be very long. So it was through research, they built better materials, they built better profiles for wind turbines, for airfoils, and so on. So it took a lot of time to figure it out. I think wave power will have to go through this. And that's why it will take 10 to 15 years to get wave power. Space. If you look at, a specific amount of power generated by, 1 meter square of space in coal or gas industry, you would need 100 times that space to generate the same amount of power when you use wind and solar. or you would need 50 times that space instead than when you're using coal. But I mean, if you have a building of 5 or 6 floors, you cannot just install solar power on top of it and power all of it, because you need much more space than its roof to generate enough power, for a building. I mean, usually like 1-2-story home, maybe for a regular household, you need probably about 12 to 15 panels of those solar panels. So we don't have enough space, especially in small places or crowded places like New Jersey. We don't have enough space for solar and wind to generate the power needs. We need to look at other resources, and wave power can help. I talked about wave power to solve the problem of the grid or to support the grid, but wave energy can be used for other things. It can be used to charge underwater vehicles. It can be used to charge ocean observation systems. You could place these things in the ocean somewhere far. They could operate autonomously. They could do a lot of things on their own. You could, it takes a lot of power to move power around, like to move gas or fuel to an isolated island or isolated community. It's a lot of power. So the cost of power becomes even much higher. I mean, Hawaii is probably one example if you want to think about it. So wave power could be used to support isolated communities. As we talk about coastal communities, in the face of extreme events, storms, hurricanes, and so on, you could use wave power to support the coastal communities during disasters and during disaster recovery. I mean, like yesterday, or 2 days ago, all of Puerto Rico lost power because of the hurricane that hit it. So, one had access to wave power, one could use wave power much faster than other power sources. You could use wave power for desalination. This is very important. You put water and energy together. You could use, if the energy is almost free, like, ideally speaking, because it's there, it's available, it's renewable, then you have the water, you could use it for desalination and reduce emissions, CO2 emissions. You could use wave power for marine aquaculture, to operate fisheries and so on. You could use wave power for seawater mining and so on. Because these are independent uses that you don't need to connect them to the grid, the outlook for its implementation is about 5 years. New Jersey, its latitude is at 40 degrees north. If you look, most of the wave energy around the world, or wave resources as it's called, is between 40th and 60th line of latitude, north and south. So, New Jersey has actually a significant amount of wave power. So does the West Coast, where they have even more power than New Jersey. Okay, how do we generate power from waves? I'm going to give a few examples here. You could put this what's called the, here oscillating water column. You could see the structure in there. As the waves hit and as the wave crest hit, the water rises. As a wave trough hits, the water falls. This motion of the water up and down, it could push the air that is in that closed chamber. As it pushes the air in and out, it rotates a turbine. And it's pretty straightforward. The overall efficiency depends on the air turbine. I think some of the operating oscillating water columns, one of them is in Spain, 2011. It was integrated with a breakwater, just on the side of the breakwater. I think New Jersey might try something like this soon. So it has 296 kilowatts. It supports 250 households. Other operating systems, that one was decommissioned. Other operating systems are in Italy, South Korea, and Australia. They generate, anywhere from 200 to 2,000 kilowatts, something like this. Actually, in New Jersey, there is a company called Ocean Power Technology. It was the first one to install something. I think they call it Power Buoy P3 or something like this. In 2005, they installed it 22.5 kilometers offshore, and they still generate about 7.5 kilowatts from it. Now, you could say, well, 7.5 kilowatt and so on, and we need, thousands of megawatts sometimes, something. But you can imagine you could install hundreds of these or thousands of these, and that's where they call them, wave energy farms, and get a much larger system. Heaving buoy in Sweden was installed 2 kilometers from coastline, some of them in Denmark and in Gibraltar. I'll talk about general efforts at the Davidson Lab. We had a project funded by the USAID in collaboration with Virginia Tech, where we had a wave energy converter. By that motion of wave energy converter, we pushed a crank. The crank pumped the salt water up a system. It passed it through a membrane, and then we got fresh water out of it. So without any generator or anything, we just pumped it, and there was an accumulator to help push the pressure so that we can push it through the membrane. Right now, we're working on a variable geometry wave energy conversion and control system. Dr. Datla is doing a lot of testing on the system. We built all of it here at Stevens. I'll not talk more about this. So let me talk about barriers to wave energy. Some of the barriers include, we don't have a dominant design yet. Why? We don't have the best technology, that's one thing, but also, waves are different in different parts of the world. And designing something for a specific wave that might work, it might not work for a different wave spectrum or waves of different characteristics. So that is, we don't have that. And I don't think we will have one dominant design like we have with wind turbines. Environmental impact and regulations, we have a lot of standards on this, but still, one needs to work on those in order to enable placing them in water. And I should say that, testing a wave energy converter in full scale in water is very expensive. Also, placing them there, doing grid connection, port facilities, operation and maintenance costs are very expensive because they're in harsh environment. Seawater corrodes everything, or impacts everything in a different way than air. In the ocean, the waves vary very much, and you could design for a specific wave height, but then the 50-year return could happen, within 1 year or something like this, and one has to worry about, the harsh environment wave energy converters working. Planning and licensing, I think we need more policy on that and more support. Industry engagement. Industries, they're not ready yet to put the big bucks to be able to do wave energy conversion because they worry about profit more than anything, which is understandable as well. So government can play a major role with robust investment in research, innovation, and education with long-term objectives. I will stop here, and let's see how for now. How are we doing on time? Okay.
We're doing good. It's 5:30, so you have another 20-25 minutes.
Yeah. So I'll take questions if there are any questions. Are there any questions? Yeah, Jessica.
Hi, thanks for the presentation. It's very interesting. I'm wondering, I know there's not like a standard design yet. Does it emit any sound? I know that's been an issue with like deep sea fishing and things, like the amount of sound that boats emit causes issues for wildlife. So do you know if that's something that you guys are considering in design or people are designing?
Yeah, we have to consider that in the design. We have in the design process, we can only estimate it and talk about it. We have what's called NEPA, something from the EPA, and we have international standards for the designs on all of these things, and we have to satisfy those standards in the design. But then at the end, you place it, and you have to do measurements, and then you have to decide if the design predicted the acoustic noise and so on to an acceptable level. That does not impact, species, marine species.
Cool. That's good to know. Thanks.
Thank you. Gabriela?
Gabriel.
You mentioned Puerto Rico and the energy.
Can you please raise your voice? I'm not hearing.
Sorry. Do you hear me well now?
It's still like faint. They come closer to the microphone, I guess.
Okay. Is it better now?
Yeah.
Yeah.
Okay. You mentioned Puerto Rico and the energy shortage the country is facing now. Would the structure of wave energy be more resilient to climate events such as hurricanes than structures of solar and wind? Because I imagine that the pressure over the system can be really high either way.
Sure.
Right?
Yeah, that is a very good question. So a part of the design is a risk assessment, how it performs in a hurricane or something like this. So the one I'm going to talk about system, what you would like to do is to take the whole system and kind of push it down into the water so that it doesn't feel the hurricane forces or waves. And when the hurricane passes, you kind of push it back up to operate again. Risk assessment and risk management is a big part of the design of these wave energy converters.
Anisha.
That's a very good question, Gabriela. Thank you.
Hello, hi. This presentation is very interesting. I just had a question. So a couple of weeks ago, I did see that UC Berkeley was doing similar research in the TEF lab, but they had their device on the ocean bed floor, and they were using the movement of the bed floor during the waves to generate electricity. So I guess my question would be that, did you go through like a process of different methods of where the device, the piston, all of that was placed oscillating, and then at the structure, like at the top of the ocean? And is there like something that you found out, which was it was better to do it on top of the ocean waves or oscillating in between the ocean? Was there like a process that went through that?
Very good point. I think the system tested in Berkeley is a system by a company called CalWave, and it is underwater. If you put anything underwater and you have to go fix it, it's much tougher to fix.
The cost of maintenance, yeah.
Yeah, its maintenance is much tougher. One of the innovations about what we did is to place what's called the power takeoff system. The power takeoff, what takes the power to generate electricity, is to place it above water, as I will talk about it. So this way, if you need to fix a component, if you need to go do something, it's much easier to do it when it is in the air. I think DOE likes that aspect of our design very much.
Understandably. Thank you.
Thank you, Anisha.
Mohammed, I have a follow-up on Gabriela's question. Actually, she was talking about hurricanes and when this weather is rough, the sea is rough. How do these things stand up in rough weather? Does the performance get weaker? Because looks like these are pretty lightweight equipment, right?
Yeah, I mean, as I said, yes, you design them let's say for 2 meters. And, that's where you generate energy. Now, if one wave passes like 4 or 5 meters, let's say, it's okay. But if you're going to have a wave of 8 meters or 10 meters, what you want to do something. So the one I will talk about, you have these 2 flaps. You can put them down and keep them down so that there are no wave forces significant on them. When you put them up like this, the waves will move them back and forth. So you put them down and then they're not going to feel the waves. And they could still be at a level where they could be impacted by the waves. So you drop them down more in the water. The system we're designing is to operate in deep water, where the wave velocities and the wave pressure and everything drops exponentially with depth. So once you put it a little bit deeper in the water, it will not recognize that there is a storm above it. This is a part of the risk management, risk assessment, and design as well.
Okay, all right.
Yeah, we will present these things. We studied them actually.
I'm gonna go to the next section.
Sure. If there are no questions, we'll move on. So I'm going to talk now about the design. I will not talk about the specifics of the design as much. I will show how much of it is involved in here. Okay. But before I do that, let me acknowledge the support of the Department of Energy and the program EE00088853. This is a team effort. We have few people from Stevens. We have few people from Virginia Tech. Dr. Lei Zhu is leading the effort there. He's now, he's moved to Michigan since we started. We have, the scope is to design, as I said, frame and PTO, mooring system, models testing, hydrodynamic analysis, LCOE. But with all of this, we will take into consideration relevant industry standards. We will take into consideration environmental requirements as required by NEPA, and we will talk about installation and operation plans, as well as risk assessment and management. Three companies, I forgot to mention Resolute Marine Energy here. It's a company that also supported the effort. So when you start such a project, you have to have a goal. Our goal is to design 100 kilowatt annually average WEC, that's wave energy converter, to be tested at the Packwave South site in Oregon. This is a site that the Department of Energy has funded in order to test all of these wave energy converters. They have not tested anything above 100 watts up till now. But I think soon they'll be testing up to 5 kilowatts or something. The 100 kilowatt test might take a couple of years to decide on it. But our design could be tested there at that point. So our innovation is to have a floating system that can be deployed in deep water. Another innovation is to have a controllable PTO and a tune system for broad market application, a tunable system. Like we're going to design it, but we can change its geometry, we could change the separations and so on in order to be able to place it East Coast, West Coast, Africa's coast, South America, wherever. Our targets are to increase the capture width ratio. That is, capture width ratio is the power that's caught by the wave maker relative to the power that's coming to it. And we compare it with what's called reference model 5 of the DOE. We want to increase it. That one is 18%. We want to increase it to 40%. We want to reduce the peak to average ratio. And that's a big problem in these things. And irregular waves, sometimes you get a very high peak of power and then it goes low. So we want to do something in the design to reduce that ratio. And we want to reduce the levelized cost of electricity by 40%. So those are our targets. Okay, let me mention one thing here. It's really, for these systems, it's really very hard to say, yeah, I can prove it in the lab, it's going to work in the ocean. Because I might not find the generator I need to go put it in the ocean. I might not be able I could design something that works here with 3 screws. It might need 20 screws when I place it in the ocean. So full-scale design is our aim. We're not going to perform a model test and then take it up and scale it up. And we will use the tests only to validate simulations and identify pitfalls. By the way, these names here are the names of the people who work on the different aspects of it. So I just want to make sure that I recognize their work. These are all students who have worked on all of these aspects, and the Virginia Tech students have worked few times here. This is the design. This is how we expect the flaps to move in the water. And we did some testing and they move as such actually in the tank. That's what you need. So these are the dimensions. You know, it takes a long time to decide on the dimension. The lengths actually, we changed it since we decided last from 60 meters. I think we went down to 45 meters to reduce the weights and so on, without impacting the wave generation capability very much. We're still looking at how to cover the whether we have plates or something like this. But in a full scale, the flap height is 7 meters, the flap width is 12 meters, and the flap length or the flap width is 12 meters, and the flap thickness, I don't see it here, but it's about 0.5 meters or something like this. So the mass of the whole system is probably about 200 tons or something like this. So this is how we designed the PTO. It's called the mechanical motion rectifier, MMR, and we're going to do it in an active way. You could see he reverses the way he moves his hand, but the output is that it's always moving in the same direction. And this is because of a system where it engages and disengages, and it rotates whichever one it needs to rotate. So this is like the background. We've since designed it and we do it in control and so on. Like we have to look at the generator. We identified this generator in here, 200 kilowatt, 1200 RPM. Just to give you an idea, 1200 RPM is a very high RPM. If you have the flap moving back and forth, it's moving probably at a period of 10 seconds. That's extremely low frequency. So we have kind of to design that gearbox or gear system to increase the rotational speed that we get out of the flap so that it matches the rotational speed of the generator. But when we look at generator, we look at everything, including its cost. What we want to do for those of you who are in structures, we want the two flaps to work against each other out of phase. By working out of phase, the forces acting here at the hinges are reversed in opposite direction. When the forces are in opposite directions, the loads or the motion of this platform is reduced significantly. It doesn't move very much. And this is one advantage over the one flap system, which is the reference model 5. Okay, we're going to place it in the deep water, so we have to moor it. So the platform is going to have to be moored to the seabed, and there are different ways of mooring it. We looked at catenary mooring and catenary mooring with floaters and so on. We have to design all of this. We're working. So this is the high-speed tank, and now I'm going to talk about some of the tests. So we're doing these simulations to validate what our hydrodynamic simulations are doing. So we built a wave maker in here, a wave energy converter, and we put a generator, we put the whole PTO system on top of it in order to measure the generated waves. Okay, and this is not an easy job. I mean, we put it out in the shop, we bring it down to the lab, and then we place it in the water. This is a significant effort. And this is how it moves in the water. This is a free decay test. We do the free decay test to estimate some physical quantities that we want, like the damping ratio, added mass, and so on. We do these free decay, and then we do some forcing test where we move it in still water to estimate the forces acting on it, even in still water, because we need those for the design. This is now how it's moving when we have waves, hydrodynamics. You can see it. And then we look, different wave heights, different wave amplitudes, and we look at how it moves in these waves. Yeah. And we changed what's called the draft and so on in order to look at what happens when we change the location of the center of buoyancy of the system. We have to do a lot on the control of, that involves a lot of electronics and codes and so on. We're designing all the boards and electronics in order to operate the clutches and so on. And, when something is moving at a certain speed, when the flap is moving at a certain speed with a certain momentum, sometimes the waves, because it's not forcing it anymore, it's changing direction, the wave could force it to stop before to move at a lower speed. So at that point, we want to disengage it and let it move by its momentum and keep the energy flowing and then engage it later on with the wave. So this is what this whole control system is about. It's a very significant effort. These are the simulations, what we do. So we take the wave resources, what resources are available, waves period, wave heights, and so on. We add the simulation tools, different levels of simulation tools, and then we estimate the absorbed power. This is how wave resources are usually given. That is the energy period or significant period and significant wave heights. So at the back wave south, most waves are between 9 and 11 seconds, and they have a wave height between 5 and 2 meters. And when we look at waves, the height and t is one thing, but when we could look at their energy, it's ht squared actually. So, because of this, the energetic waves are between 8 and 9 seconds and 1 and 2 meters high. So we designed this system based on some specific calculations, and then we run some high fidelity. What we call high fidelity, we're solving the whole flow dynamics around the wave. We're solving, I don't know, probably 10 million equations, if you want to think about it like this, or we're solving one equation 10 million times in order to do these simulations. Yeah. So we do this, and then we validate our simulations in here, as you can see. And we do different levels of simulations. That's what I mean by multi-fidelity simulations that allows us to say, okay, I could spend 27 hours to get the answer within 5%. I could spend 3 hours to get it within 11%. 3 hours seems good because otherwise it will take me a month to get an answer. And by the way, we could do better than this. So these are the simulations. And in the end, I want you to see this. We could take the model. We could solve those 10 million equations over 17 days to get here the red line. Or we could develop a very much reduced order model, one equation actually, with a little bit of, with a few parameters. And we would get the blue line in here and in 13 minutes. So we could reduce the 17 days to 13 minutes. So if we have to run 1,000 simulations, you could see how long it will take us. And we could do this rather quite well. And you do this at the early stages, and then in the end, you validate the full scale design. This is what comes out of it, is absorbed power. From the waves by the system, we estimate the absorbed power to be 4.59 gigawatt hours. Then we say, okay, at these levels, we cannot let it operate. That's what Dr. Sarkar was asking about. At 6 meters, we can only take 400 kilowatts out of it. We're not going to take 1,600 kilowatts because we have a limit on operation. So we estimate these things and so on. We end up with annual energy 2.606 gigawatt hours or electric power of 235. This is based on harmonic forcing, that is sinusoidal forcing. If we do irregular forcing, it'll probably go down 200 kilowatts. Then we can do costing. There are codes and there are algorithms that are given by the Department of Energy where we could estimate the cost for the flaps structure, the cost for the PTO, the cost for the mooring, and then we come up with the levelized cost of electricity for one of them, We could reduce it significantly for 10, for 50, for 100, we could reduce it. And that is very important for our estimating. So I hope I gave a big, a big picture about what we're doing. I just want to mention one more thing. Designing such systems is very hard. One screw could be just a bad screw, and it could fail, and one would assume that the whole system failed, which is not completely true. So we're looking at components design. This is very important. Then DOE wants us to do this. So we're designing very, very specific components. So I'm going to stop here and see if